Now, so that's one approach, is this sort of big, hairy processor that attempts to execute multiple instructions from a single program at the same time. A different approach is basically to make the evidence, the existence of these multiple functional units just explicitly part of a program. So this is a SIMD, a single instruction multiple data. I have one instruction, and then I have multiple functional units. And maybe the easiest model to think of is vector arithmetic. So you might have an instruction over here that said vector add vector A plus vector B equals vector C. So think of these as like the add instruction for registers, except that each register, instead of being a single value, now is a whole vector of values. And when you think of writing a program that way, you can see that, in fact, if I have a different functional unit for each element of the vector, I can get a lot of parallelism. So I don't have to search for parallelism. Now the programmer is telling me explicitly by using vector arithmetic that you can do all these vector adds for each element at the same time. Those can be done in parallel. So these SIMD architectures are very attractive because the hardware is very straightforward. There isn't a lot of searching for something that can be done at the same time. We basically give you an instruction set where you can say, I've got a 1,000 element vector. I want to add it to another 1,000 element vector. There you go. There's 1,000 adds that can all be done in parallel. And if you've got 4 functional units, you should be able to do it in 250 cycles. So this is sort of neat. In fact, it's so neat that there is a question about conditional execution, which is interesting to think about. So suppose you say, if element I is bigger than element J, put a 0 in, or if A sub I is bigger than B sub I, write a 0 in C sub I. You say, oh, I can do all that in parallel. The trouble is that if you think about doing it in terms of a compare and a branch, there isn't one program I could write, right? Because some of these guys will say, I'm bigger, I'm going to branch, and other guys would say, no, I'm not bigger, so I'm not going to branch. So there's a sort of notion of, oh, well, how do you deal with sort of conditional execution? And the way the processors deal with it is they actually, instead of branching, you simply set a flag. If A is bigger than B, A sub I is bigger than B sub I, set the flag. So some processors will set the flag and other processors won't set the flag. And then you have these conditional execution things that say, do this if flag 1 is on. Now all the processors can do that in parallel. Some of them will have the flag on and some won't, so some will actually do it and some won't. But you only have one program that's able to do data-dependent execution in each of the separate functional units. And in fact, a lot of modern processors, because branch is just so expensive, right? Branches, every time you do a branch, you have branch delay slots and annulments that have to happen, bubbles in the pipeline. It might be simpler, particularly for very short little chunks of code, 1 or 2 assembly language statements and an if, to actually do this conditional execution. No branches involved, right? So there's no disruption of the instruction stream. So it might actually work better to do this sort of conditional execution hack. So they're starting to appear in most modern instruction sets, this notion of a conditional thing. Now you guys actually own a big SIMD unit in your Intel processors. They come with one of these built in. It's called the multimedia instruction set or SSE instruction set. And think of that as it's a big ALU and a big register file. This particular device only, it only does register-to-register operations, right? So loads and stores. So there's the program that's running on the ordinary processor. So this is a separate coprocessor sitting off to the side. Is the ordinary processor is the one in charge of loading up these registers and storing them to memory. But once information is loaded into the registers, you get this special unit that's capable of doing arithmetic between these registers very quickly. You sort of go, well, can't an ordinary processor do that? And the answer is yes, but the neat thing about these SIMD units is they're able to do a 64-bit operation or 2 32-bit operations in parallel. And you say, well, how does that work? Well, you just take the 64-bit ALU and you come along and you cut the carry line between the bottom half and the top half, and now you have 2 independent 32-bit ALUs. And you can keep doing that. You can turn it into 4 16-bit ALUs. So a lot of the graphics acceleration you do, or multimedia encoding and decoding for watching movies, or encoding your voice in Skype calls, whatever. Now we're working on 4 4 different operands in parallel. So, 4 16-bit operands. Same basic hardware, we're just fooling a little bit with the carry chains to reuse it to say, look, think of this as 4 16-bit numbers. So a lot of the video encoding stuff is, working on, for example, these little 8x8 macro blocks. And there's operations, that's 64 pixels. There's a lot of operations that are happening in parallel on each of the pixels. So if you thought of that, think of this guy as dealing with 4 pixels at a time. Right, so now we're actually using one instruction, just a SIMD unit. One instruction is actually operating on 4 pixels. So instead of taking 64 operations, it'll only take 16 operations using this unit. And that's why these coprocessors are there, because a lot of sort of multimedia stuff these days that can take advantage of that. In fact, they go all the way down to 8 bits. So then the instruction set, look, do an add, but think of all the operands as 8 bits, or think of them as 16 bits, or think of them as 32 bits, or think of them as 64 bits. So you actually write these programs that, instruction by instruction, sort of tell the machine, should it think itself as one big 64-bit machine, or should it think of itself as 8-bit machines? It's a really neat idea, and it works very well. It's a godsend. I've been able to do a lot of real-time digital signal processing. So if I can write programs that run on these, just a standard laptop that are able to, basically, tune in radio stations completely in software. Specialized instruction set is a special program. We write our routine specially to use this instruction set, but it's worth it for something that I'm going to be doing day in and day out. So SIMD was a great idea. It's not general purpose. These are accelerators for very specific sets of operations.